Hi, can everyone hear my voice? Okay. We'll start our class at 10:33. Okay. I think there are 20 participants right now. So I'll start the class today. Can you guys see my screen and hear my voice? Okay, thank you. Hi, I am TA Jian Kim, and today we'll be starting our lab session on GPT and BERT. So for today's contents, we will be training a mini GPT from scratch, and we will conduct sentiment classification using BERT. So, Okay, we don't want. So first, please install the necessary packages. And import the packages. And for training our mini GPT model, we will use the Open Web Text 10K dataset. So use this load dataset function to pull the data from Hugging Face. So if you run the code, the data looks like this. It consists of the text feature with 10K rows. And now we're going to split the data into train valid test. And we're going to use this train test split function to split our data into train and valid plus test. So we're first going to split it into train and valid plus test. And then we're going to split this test data using the train test split function into valid and test again, using the valid test ratio. And we set this seed so that it is determined. So if you run this code, it would output the split data into train and valid and test. So you can see that the output shows 8K, 1K, 1K train valid test. And the train data set looks like this. And the first train text sample looks like this. And now below, we're gonna define a tokenizer. We're gonna use the distill GPT-2 tokenizer and define a preprocess function. So as you can see below in this code, we're gonna loop through for each of the train valid test in this split data set that we defined. We're gonna run this preprocess function with 4 processes. And this preprocess function, so we have our sample text data stored as 8K rows. For each of the rows, we're going to split it into double new lines because as you can see here, the sample text data shows double new lines. So we're going to split it and join it with a space. So this double new line is converted to a single space. And the result of this is a list of the entire text data. So for train, it would be 8K datas. And if we run this function, it would tokenize the data in the list. So if you run the tokenized split data that we defined here, it shows that the result of this tokenizer is input IDs and attention mask. So there are these 2 features, and we've removed the previous text feature. So it shows 8K rows of input IDs attention mask. And this shows the first input ID sample is long, so I've truncated it to 30 tokens. And the first input ID token length is 220. Oh, okay. So someone asked me to make the text larger and okay, maybe I'll switch to another screen. Okay. So I'll continue. Um, okay, we talked about the tokenized split result until here. And now we are going to group the texts using this function. This function over here basically splits the text into a fixed size. So we're going to define a block size of 128, and we're going to split our text so that each text would be size 128. And we have tokenized split, train valid test. We would be looping through each of these train valid test and applying the map function using this group text. So if you look at the code over here, it shows that we would be, the K here is input IDs and attention mask, but basically we won't be using attention mask, but still we'll just leave it here because there's not much computational difference. We will sum all the input IDs of these 8K rows. So it's initially 8K times sequence that is different by each row. So we will sum all these tokens into a single list. So we will concatenate all the tokens and measure the total length of the concatenated tokens. And the concatenated token list is definitely greater than the block size -2. So we will divide it and multiply it so that this total length is a multiple of block size -2. And the reason for -2 is because we're going to add the BOS token and EOS token on each end. So this code shows that we are going to loop through the concatenated samples by block size -2, and we're gonna add BOS and EOS on each end. So this results in 128 block size for each sample. And so we can run this code. And yeah, you can see that initially it was 8K, 1K, 1K, but after splitting it into block size 128, the train valid test is 68K, 9K, and 8K. And this is a single sample, single token list sample. And this shows that the input ID's length is 128. So we have okay, over here, we're going to convert the input IDs into tensor. So we're going to create an empty list and append all the input IDs values for each train valid test and convert it into a tensor. Okay, so this shows the results. It is a tensor of 68K and 128 tokens for each row. And when we decode a single sample of the training set, it shows that there is 128 tokens and the BOS and EOS token on each end. Okay, so this is the BOS and EOS token. And now we're going to implement the causal language model. So in the last class, in the last transformers class, the transformer model consists of an encoder and decoder, but for causal language modeling, we only would be implementing the decoder layers. So there is no encoder and only the decoder. And usually in the original transformer model with the encoder and decoder, the decoder model consists of self-attention over here in between the masked self-attention and feed-forward network. And the attention in between was to apply attention on the encoder and decoder side. However, we don't have the encoder, so we will not be using that. And we will only be putting our data into the masked multi-self-attention and feed-forward network. So first, import the torch modules. And this multi-head attention class we will be building upon the code from last week. So this multi-head attention class is the same class as last week, and it shows that we can compute our QKV using our projection, QKV projection on queries, and we can compute the outputs using these QKVs. So this function has the multi-head attention dot product and outputs the attention output. And for position-wise feed-forward network, it consists of 2 linear layers. So we have our ReLU activation function and we input our X into the first linear layer defined and apply dropout. And then we would be putting this input X again into the second linear layer and apply dropout. So This is the multi-head attention class and position-wise feed-forward network. This position-wise feed-forward network is used here. And then we have our sinusoidal position encodings. So this is also the same code from last week. We have a deterministic encoding, positional encoding using this sinusoidal positional encoding. So basically, as you can see here, this position encoding is added to our input text in this stage. Okay. And now we'll be implementing the decoder layer. So the decoder layer is this single layer over here. We have masked multi-self-attention and feed-forward network with residual connection and layer norm in between. So first, we apply attention to our X. We compute attention using our multi-head attention class defined above. And then we apply dropout and residual connection. So this plus sign over here. And then layer norm. So this layer norm is added to the input X. And then we take this X and save it for residual connection again later. And then we apply this X to position-wise feed-forward network, which we also defined in the above classes. So this feed-forward network. And then apply dropout and add our residual connection to X. And then we put this X into the final layer norm. So this decoder layer shows that our input is put here and processed by these layers and then output. Okay. For our decoder class, our decoder class is this entire part. So we first add positional embedding to our text. So our sinusoidal positional embedding, and then we will be putting through the X processed input into decoder layers. And in this figure, it shows 12 layers, but in our lab session, we'll be only using 6 layers. So this decoder class shows that we put our input IDs into, we compute the position by position sinusoidal positional embedding and embed our tokens, embed our input IDs into tokens and add the positions. And then apply dropout, and we have our self.layers here, which is a module list of decoder layers of 6 decoder layers, which we define in our config. So this decoder layer is implemented here above. We put the X into each decoder layer. And now we are going to implement the GPT model. So first, in this init function, please create the decoder embedding, the decoder, and the prediction head. And in the forward function, generate the causal mask and put the input into decoder layers and output through prediction head. So I'll give you a few minutes so you guys can implement it. Okay, I'll start writing the code. Okay, this takes too much time, but we have a lot to do. So I'll first copy paste the code and then explain. Here we have our decoder embedding, and this is defined to define an embedding for our decoder. So up here, you can see that in the init function, we have to define an, an embedding to embed the tokens. And this is used to embed the input IDs. So we first define the decoder embedding, which has a length of tokenizer and our embedding dimension. And then we define our decoder, which takes the configuration and the decoder embedding. So as you can see in the init function here in the decoder, we have to put in the config and embedding. And then we define the prediction head. So after we get the output of the decoder, we would have to put it through a linear head of size tokenizer so that it predicts the next token. So after we defined our decoder and prediction head, now we will go on to the forward function. We will first generate mask to pass to the decoder, and we have our input here, our input and the mask put through the decoder. So in our forward function, you can see that we need to put our inputs and the decoder causal mask. So we take the decoder output and then put it through the prediction head, which is a linear layer for next token prediction. And then since we've defined our GPT model, now we will be training our model. First, import the necessary packages and set the configuration. So we will set it similar to the attention is all you need paper with embedding dimension, feed forward dimension, and attention heads of 8, max positional embedding 1 to 8 decoder layers of 6. We set our learning rate and batch size and put the tokenizer and config into GPT because in our init function here, we need to put tokenizer and config. And then we put the model to our device, which is GPU, and set our optimizer to Atom by passing our model parameters and learning rate, and set our criterion to cross entropy loss because we would need to predict among the tokens. Okay. And since we've defined our model, optimizer, and criterion, now we will define our data loaders. So for train, valid, and test, we initially put our data into this web text dataset dictionary. So as you can see here, it consists of sample size times 1 to 8, which is the token length. So for train valid test, we each have these tensors. And we will wrap it with the data loader so that this train valid data is iterable with batch size as defined. So After defining our train valid data loaders, we will define our functions for training and evaluating. And we loop through the data loader to take each batch and put the batch data into device. So this would be batch size of 64 times 128. And we put this data into the model to get our logic predictions. And then we zero out the optimizer so that the gradients are not accumulated. And for our targets, since we are doing next token prediction, we would have to shift the tokens so that the ground truth target starts from the second token. And for the logits, since the logits are generated starting from the second token of target, we will have to match the size with target. So we would take the logits until the second last token. And we put the logits and target outputs into our cross entropy loss and compute our loss and update our model parameters. Then we have our evaluate function here, where we wrap it with no grad, and we loop through the valid data loader. We put each batch into our device and output the logits by inputting this target data. And again, we shift our ground truth targets and our logits and put these into the loss function. And this code now trains and evaluates our model. So it would take quite some time, so you guys can train later. So I'll be switching to the solution file so that we can look at the other examples. Okay. Oh, actually, I'll just switch back. Sorry. Okay, and we can now compute greedy decoding. So please implement the greedy decoding function. So we would first need to get the model output and then find the maximum value for our predicted tokens. So for the model output, get the maximum value and then get the last prediction, which is our target, and concatenate the greedy decoded token, which is the last prediction and our initial input sequence of tokens. So please implement this greedy decoding function. Oh, and in our position-wise feed-forward class, please remove the residual connection that is added to X here because we will be adding it in this decoder layer class. So in your provided IPYMB files, please modify this position-wise feed forward so that there is no residual connection here. Okay, now I'll start implementing the greedy decoding code. So as you can see here, when training the model, you can see that the validation loss is decreasing. So I'll stop running this training code cell for now. And for greedy decoding, we will put this no grad wrapper and provide the input and put the input into the model and predict the next word by applying this max function because we would need to select the maximum value among the total tokenizer length embedding dimension size. So the tokenizer length dimension size, among the tokenizer length dimension size, we need to select the maximum for the next word. And then we will be taking the last prediction. So this would be the next word. And then we would concatenate the original input and the predicted next word. And if the next word is EOS token ID, we would break it because we initially trained the model so that the input data set has EOS token in the end. So you can run this greedy decode code. And from the test data, I am randomly choosing a sample. And for the first 20 tokens, I am inputting this into the model. So I am greedy decoding based on this prompt, the first 20 tokens. So this test data, the first 20 tokens are put into this greedy decoding function with the model, and it would predict the next word iteratively. So since we only trained the model for a few epochs, the result shows that it doesn't really make sense over here. But if you train it more, then it would be improved. So you can see that this is the prompt that we give the model, and the model starts prediction starting here with greedy decoding. Okay, so now we'll move on to BERT. So BERT is a bidirectional encoder representation for transformers, and BERT is trained to mask 15% of the tokens, and the tasks consist of, there are two tasks, which is masked language modeling, MLM, and next sentence prediction. So for masked language modeling, we mask out 15% of the text tokens, and we predict the masked tokens based on the other context. And then for next sentence prediction, we are provided two sentences, and the task is to predict whether the second sentence is the next sentence of the first sentence. So the BERT model basically enables training the context of the text. And first of all, we'll be conducting sentiment analysis with BERT, so please install the necessary packages. And import the packages, import necessary packages, and set random seed and the device. And now we will download this reviews.csv data, which looks like this. It is a Google app review data set. And it shows that in this content column, it shows the reviews of each user, and the scores show the scoring for the user. And if we use this dataframe.info function, we can see the column names and the column types. In this lab session, we'll be using this content and score column. So we can plot the score column, and it shows this distribution. So there are 1 to 5 for scoring, and this shows the histogram for the data frame. And we will define this toSentiment function, which is used for multi-class classification. So basically, in this code, we will be inputting the content as input, which is the user reviews. So I cannot open the App Store anymore, and the score 1. So we will use this content, this review content, and we will convert the scores. So initially the scores were 1 to 5, but we are going to create 3 classes among the 5 scores. So negative, neutral, and positive. And if the rating is less or equal than 2, then it is 0, and which is negative. And if the rating is 3, it is neutral. And if it is 4 or 5, then it is positive. So we apply on this score column in the data frame, we apply this toSentiment function to get our sentiment column. And now you can see that these score reviews are converted into sentiment, which is negative, neutral, and positive. And it shows the histogram. Now for data preprocessing, we will use the BERT-based case model for our tokenizer. If you run this sample text, you can tokenize it using the .tokenize function or the convert to token IDs function. So, okay, this shows the tokens of our sample text and our token IDs and our sentence. And we can access the SEP token and CLS token. We can access the special tokens using this .sep token or .cls token in the tokenizer. And we can also create tokenized encodings using this encode plus function. So this encode plus function returns the input IDs and attention mask. And if we put in our sample text, which is defined here, we can set the max length to 32. So we can set it to we can tokenize into a fixed max length, and we can add padding if the sequence is, if the number of tokens are less than 32, and we can truncate it if it is more than 32. And we also can add special tokens such as CLS or SEP. And now you can see that the encodings for the input IDs, the length is 32, and this shows the padded input IDs. So we set our max length to 32 and pad to max length as true. So that's why this is the original input with our special tokens added, and the rest is padding. Mhm. And this is the attention mask. So it shows 1 until the number of valid tokens and 0 for the padding tokens. So we use this attention mask so that we tell the model that only this part is where the model should look at. So we don't want the model to look at the paddings because it's useless. And we can convert the IDs into tokens. So it shows that these input IDs are like this if we decode them. So it has CLS and SEP added on both sides. Next, we can choose the sequence length. And when choosing the sequence length, you can either just use the max size for the model, the pre-trained model. If you're using pre-trained BERT, then the pre-trained BERT is trained on a fixed sequence length. So you can basically just use that maximum length, such as 512 or 256. But you can do something which is a bit more compact, because considering the input data, you might not necessarily need the 512 token length. it might be just too much and too much padding and just unnecessary memory usage. So here you can see that the DF content was the review column, so the review text column for the users, and we encode each of this review text into tokens and set the max length to 512. So, and then we append the length of the tokens into this list so that we can get the length of each review, the token length of each review. And as plotted below, you can see that the token lengths are generally less than 150, and this is just way less than 512. So we can just set the max length to 160. And now we are going to build the dataset class. So for our reviews, this is the review text of the users in our reviews column. And the targets are the sentiments that we defined. So the three classes and the tokenizer and the maximum length. So this dataset class gets the item index and retrieves the review text based on the index. And we also get the target based on this item index. And then we use this tokenizer to encode our reviews. So we encode this review index retrieved from the index and add special tokens and set the max length and pad to max length. And for the return, we would return the reviews, which is the original review text of the user, and the input IDs, which is the tokenized input IDs and the attention mask, which shows which part is the padding and which part is the actual content. And this target is the sentiment, the three class sentiment classification labels. And then we define this DS using GP review dataset. So we take the content column of the dataset, convert it to NumPy, which is a array of strings, and this sentiment is also converted to NumPy, where each element is 1 or 2 or 3 for sentiment classification. And we also pass in our tokenizer and max length because it is all set in our init function of the GP review dataset class. And you can see that since the data frame length was initially 12K, the DS length is also the same. And we can get the first item of review text, which shows I cannot open the app anymore. And the input IDs also is processed using this encode plus function with our defined maximum length and adding special tokens. So this is the input IDs for I cannot open the app anymore. And this is the attention mask, which shows which part is the padding and which part is the actual context. And then we will split our data into train test. So we will split the data using scikit-learn's train test split. So first set the test size. So the train would be 0.9 and the valid and test would be 0.05 and 0.05 respectively. Okay, so this is the train valid test shapes. We split the data frames and then we create the data loader by passing in this GP review dataset class. So as we discussed above, we input for our input data frame, we convert it to NumPy, the content and sentiment to NumPy, and pass this to generate the output data set. And we wrap it with the data loader so that it is iterable with batch size of our defined batch size. So we set our batch size to 16 and we put our train valid test data frames that are split here into this create data loader function. And we define our maximum length and batch size too. So the result of these train valid test data loaders would be a data loader type. And this is a single sample of the train data loader. You can see that it returns these keys, which are from this dataset class. And the result shows batch size 16 and 160 token length. Okay, so now we will implement sentiment classification with BERT. So first, pull the model from Hugging Face. And we defined our BERT model and we can input our encoding. So this encoding shows that it is a single sample. We can view the length of the input IDs, which is 32. So we can put, this is just an example. We can put the 32 sequence of tokens into input IDs and the corresponding attention mask, and it would output the last hidden state and pooled output. So the last hidden state shows one shape of 32, 768, and this 32 is the sequence length, and 768 is the hidden dimension. So the hidden size of the BERT model. And for the pooled output, this is actually, so we take the first hidden state among the 32 and we put it through BERT pooler. So if we look at this BERT model, it shows that the last layer is a linear layer. Okay, the last layer is a BERT pooler, linear layer of input features and output features of 768. And the pooled output is the result of the first hidden state, the first sequence hidden state. So 11768. So the first one here among the 32 is put through this BERT pooler, and the result is this pooled output. And we have our sentiment classifier class, which defines the BERT model and dropout and linear layer. This linear layer is used for sentiment classification. So we have n classes put here. And we will use this pooled output to classify among which classes the input corresponds to. So the pooled output is put through dropout, and then we will put it through this linear layer for multi-class classification of 3 classes. And we use this pooled output because it is basically the CLS token for this BERT pooler. And now we've defined our sentiment classifier model. And input IDs and attention mask shows this shape. Okay. And for training, so we will use the Atom W optimizer and the scheduler with cross entropy loss. This cross entropy loss is used because we're doing multi-class classification. And we define our train epoch and eval model functions. So for train epoch, we loop through the data loader. We get our input IDs and attention mask, and we put these into the model and get the output of the BERT model. And we use this output and get the maximum for prediction because we initially defined the linear layer. Okay, so we initially defined the linear layer of 3 classes, and we're going to get the maximum prediction among the 3 classes for the final prediction. And output the loss using outputs and targets, and then get the number of correct predictions and add the loss. So for our evaluate function, it's also very similar, but we just wrap it with the no grad, and we loop through the data loader, get our input IDs, attention mask, put it to the model, get the sentiment classification output, and apply max because we want to get the maximum among the 3 classes for each instance, and apply the loss function, get our predictions, and put the loss into our list. Okay, so this is the code for training and evaluating. We will loop through each epoch, and we will train the model by passing the model and train data loader. And we will evaluate the model similarly. So you can run this code to train the model. This training takes a bit of a time, so I'll just pause it here. And if you can run this to plot the training history and accuracy. So if I swap to the solution file, just for showing the results. It shows that the training is it is trained um with 3 epochs. You can train on more epochs, definitely. And the you can plot the training history. So for train and validation, it shows like this. We only trained for 3 epochs, so the validation accuracy does not increase much. But if you train to about 10 epochs, it would reach nearly 100% accuracy. And for evaluation, you can also put in the test data and evaluate the trained model using this test data. And it gets an accuracy of this much, 0.73 when training on 3 epochs. Okay, and we can also get the predictions by putting the inputs and attention mask, getting the output, and you can apply softmax to get the final probabilities. So this code is just very similar to the code above. Instead, it just adds code for logging the predictions and prediction probabilities and the targets. And based on these values stored, you can compute the precision recall F1 and support. And you can also predict on raw text. So first, this is the raw text we would want to predict. We can put it into the tokenizer encode plus function to tokenize this review and get the input ID's attention mask and put it to the model for output. And we can use torch.max on the last dimension to get our prediction among the 3 classes. And this is the review text, and the model has outputted this text as neutral. Okay. So if you have any questions, you can leave it in the comments. I'll wait a few minutes for questions. And maybe we have some time so we can go through a quick review. Um, yes, our next project, we will announce it next Tuesday. So I'll go through a very quick review. First, we have trained a mini GPT from scratch. So we did data preprocessing and we coded a decoder-only causal language model. And then we also used BERT to conduct sentiment analysis and sentiment classification. So for data preprocessing, we pull the data set and split it into train valid test. And then we preprocess the function by putting the text into the tokenizer. So for each train valid test, we tokenize the input data. We tokenize the data for the train valid test, and it shows an output like this with data sets and the input tokens, the sequence of tokens. And then we group the tokens so that it has block size of 128. So we want to split the train valid test, each of the train valid test into a fixed sequence size. And we add BOS and EOS on each end. And then the result shows the train valid test as with these increased number of rows because we split it into 128 block size. And each element in the row, each row consists of 128 sequence of tokens. And then we convert each train valid test data into a tensor. So the tokenized and split data into each block size is converted into a tensor. So this shows the shape, which is 68K times 128. And we can build our causal language model by inputting our text and adding positional embedding, and then applying 6 layers of decoders, but you can modify the layers if you want. And then the decoder layer consists of masked multi-self attention and feed-forward network with residual connection and layer norm in between. So we have our classes for multi-head attention and feed-forward network, which consists of 2 layers, 2 linear layers, and a fixed positional embedding, sinusoidal positional embedding. We define our decoder layer, which is the blue part in our figure. It consists of attention, residual connection, layer norm, and feed forward network with residual connection and layer norm, just like this figure. And then we have our decoder, which consists of this part of the model. So we put the text, add positional embedding, and then put the input into multiple layers of the decoder. So we add positional embedding to the token embeddings, and we put this input X into the multiple decoder layers. And then we can define our GPT class, which defines the causal mask for the decoder, and get the decoder output and put it through a prediction head so that it can predict the next tokens. And this prediction head has a dimension of tokenizer length. So we can set our configurations, learning rate, batch size, define our model, and then define the train valid test data loader so that it is iterable for each batch size. And for our train and evaluation, we basically put the batched input into the model, get our logits, and we need to apply shifting so that the target and the logits match. And this is greedy decoding, just sequentially predicting the next output given the previous inputs. And for BERT, we talked about sentiment analysis using BERT. We used this reviews CSV dataset. So we use the content, which is the review for each user, and the score, which is the review, which is the app score that the user gave. And we converted this 5 label score into 3 classes: negative, neutral, positive. So this is the sentiment score based on this score column. And then we can we can choose a sequence length based on the inputs of our data. So we can just use the max length of the model, but it might just be unnecessary to have a max length of model size of the pre-trained length. So we can consider our data length and set the maximum length based on the token counts that most of the samples are within. And yeah, we define our review dataset class. So this is our review text and encoding. So input IDs, tokens, attention mask. So this is for a single element in the data frame, a single row in the data frame, and we can apply this data loader. So wrap it in a data loader, and we can conduct sequential sentiment classification using the BERT model and a linear layer with n classes, which is 3 for us. Okay, so I think there are no questions. Just speechless. Okay, so you can basically train the model on more epochs because we only trained on 3. So that would be the most straightforward method, because if you train the model for 3 epochs, the accuracy is only 0.75. But if you train to up to about 10, then it reaches nearly one accuracy of 1. So you can try training your model, and yeah. Okay. So if you guys do not have any more questions, I think we can end our session here. So yeah, we'll end our session here today. Thank you.